Okay. Hello, everyone, and welcome to the first session of our webinar in this second semester of the year. It is a great pleasure for me to introduce Professor Romina Arroyo from Córdoba, and who will be now the Vice Dean of our faculty, FAMAF. So we are very happy to have her here in the same day as she's start the new functions. Well, Romina will speak to us today about complex and symplectic structures on almost abelian groups. Thank you very much, Romina.
Well, thank you very much for the presentation, Adrian. This is my first talk as a Vice Dean. And thank you very much for the invitation to all the organizers. So today, I would like to speak about this joint work with this group of women working in Latin America. Maria Laura Barberis and Jamile Godoy, so they work here in Córdoba. Verónica Díaz in Mar del Plata, and Isabel is working in Mexico, in Mérida. And today, I will speak about complex and symplectic geometry on solvable Lie groups. And more precisely, I'll be working on a class of solvable Lie groups, which are almost abelian Lie groups. Okay? So I'm going to start explain or discussing complex structures or complex geometry first, and then I am going to move to symplectic geometry. So the definition that I am going to consider today of a complex manifold is this one. So basically, we'll be working with pairs MJ, where M is a real differentiable manifold of even dimension, and J is a tensor satisfying these two conditions. The second one is the Nigenius condition. And so here I write some examples, so everybody knows manifolds admitting complex structures. And the idea of this talk is that, so then I am gonna give you more examples, and I am gonna try to explain a little bit more, but here I wanted to show that manifolds admitting these kind of structures. But today we'll be interested in only groups. So and a class of complex structures, only groups, which are called left-invariant complex structures. So here G will denote a simply connected Lie group. So a Lie group is a manifold which also has a group structure, and both structures are compatible in the sense that the multiplication in the group is smooth. So by LG, I'll be denoting the left translations. So these are this map from G to G, which takes an element H and using the multiplication in the group, so we can define LG like this. These are like important functions on G, and a complex structure is called left invariant if this condition is satisfied. Okay. And in the following, I would like to speak about a correspondence between Lie groups and Lie algebras and left-invariant tensors, in this case, left-invariant complex structures, which is the following. So in general, if you consider a Lie group, so you can take the identity point on your group and consider the tangent space on the identity point. So this is a vector space, and you can endow this vector space with a bracket, okay? And you can have a Lie algebra associated to this Lie group. So here I wrote the definition of a Lie algebra. So here I wrote even dimensional because we are interested in even dimensional Lie algebras, but this is not part of the definition. I'm going to put like this. So in general, so what is the abstract definition of a Lie algebra? It's basically a vector space. Here I am considering real vector spaces, and with or endowed with a bilinear map satisfying these two conditions. So the first one is that the bracket is skew symmetric, and the second one is a condition which is called Jacobi identity. Okay, to have this Jacobi identity is the same that to ask that these maps, the adjoint maps, are derivations. Okay, so if you have a Lie group, you can associate a Lie algebra, and if you have a left-invariant complex structure, you can think in the object on the identity point. So because J is a complex structure, this J E will satisfy these two conditions. But the good thing is that if you have all this information, so if you have the information on the right side, so then you can construct, you can consider a Lie group, a simply connected Lie group with Lie algebra G, and you can construct a left-invariant complex structure using these left translations, LG. You can construct a left-invariant complex structure. So at some point, if you have the information here, so you can construct examples of left-invariant complex structures on these on simply connected Lie groups. Okay. And the idea of this talk is try to work in design. So here I am not gonna denote anymore with E, JE. So the notation that I am gonna to use in the following, it will be this. Okay, but we're interested on a class of Lie groups, which are solvable Lie groups. And I am going to speak about solvable Lie algebras in this slide and nilpotent Lie algebra. So I am going to give you the definition, so maybe all of you know this definition, but I wanted to write, and I am going to be fast, so if you have any question, please let me know. So in general, if you have a Lie algebra, so you can consider these two series, okay? So you can consider these two series. So this is denoting the space generated by all the brackets x, y, with x and y on, I'm going to write. So this is the span generated by all these such that x and y are in G. You can consider these two series, okay? So it is well known that all these spaces, subspaces of G, are ideals, in fact, ideals in this sense, and there are some relationship between elements on this series, and we have also some relation between elements or ideals in this other series. But also, we have this other condition, which relates one ideal of this series with one ideal of this other series. So when a Lie algebra is called nilpotent, well, when at some point one of these ideals is zero. So the series stop at some point k. And if you see here, if for some k or for some j, this is zero, of course, the next ideal will be zero. So many of these ideas are going to be zero. So we said that G is k-step nilpotent if k is the first ideal in which it's the first ideal vanishing. So the previous ideal is different to zero. And analogous, we can define a solvable Lie algebra using the second series. Because of this condition here, or this property, so if you have a Lie algebra which is nilpotent, so this is going to be zero, so this is going to be zero at some k, when j is equal to k, or L. So then this is telling us that any nilpotent Lie algebra is solvable, in fact. And one important theorem says that a Lie algebra is nilpotent if and only if all the adjoint maps are nilpotent. So these are like endomorphism, they are nilpotent. Okay, so if you are loose here, no worries, because then I am gonna, so we will be working with some Lie algebras and all these definitions maybe are too much, but I wanted to introduce. And so here I would like to give you some examples. So in general, if you have a vector space G, and you endow this vector space with this bracket, so for any x and y, all the brackets are zero. So this is a Lie algebra, and if you see here, so this ideal is going to be zero. So these Lie algebras, which are called abelian, are nilpotent. So then, if we start from low dimensions, so we are interested in even dimensions. So if you have a Lie algebra of dimension 2, so you can, so one of the Lie algebras of dimension 2 is this abelian, okay? But there exists, up to isomorphism, another Lie algebra of dimension 2, which is this one. Okay, so the vector space is generated by two elements, and then if you consider this bracket and then extend bilinearly and in a skew symmetric way, so this is going to give you a Lie algebra. And this Lie algebra, for instance, so this is not nilpotent because always when you take the bracket of two elements, so you always get y. So then this ideal is going to be the space generated by y. So it will never be zero, never vanishes. So then G is not nilpotent, but if you compute the second series, so then it's easy to see that G2 is zero. So at some point, this Lie algebra is two-step solvable. So this is an example of a Lie algebra which is solvable but not nilpotent. So the converse of the of this statement in the previous slide is not true. So here I wrote one more example, which is called Heisenberg. So this is the three-dimensional Heisenberg. So this is a Lie algebra generated by three elements. So this is a basis, and this is a bracket. And computing the first series, so we can see that in the second step, so this is going to be 0. So this is an example of two-step nilpotent. And with my last example, I wanted to show you that, so these solvable Lie algebras do not exhaust the Lie algebras, okay? So there exist more classes of Lie algebras which are not solvable. So here we can take matrices of size n, square matrices, traceless, with this bracket, and this is going to be a Lie algebra. And if you compute the first series and the second one, you're going to get always G. So this is not solvable, therefore it is not nilpotent, and these are called semi-simple. Okay. So what happened so what is known about complex structures on solvable Lie algebras? And here I would like to start from low dimensions and try to explain why we had so we restrict ourselves to this class of solvable Lie algebras, so the almost abelian Lie algebras. So here I wrote the two conditions of having a complex structure at the Lie algebra level. So in dimension 2, so we have two Lie algebras up to isomorphism. The first one is the abelian one, and if you see the abelian one and you want to construct an endomorphism satisfy these two things, if you consider the Lie algebra, which is abelian, so all of these summands are going to be 0. So then in order to construct a complex structure, you need to have an endomorphism satisfy this condition. And if the Lie algebra has dimension 2, I don't know, maybe, so this is a basis, so you can consider this endomorphism, and you are going to have a complex structure. So abelian Lie algebras of dimension 2 have, and of any even dimension, you are going to construct complex structures easily. And if you consider the other Lie algebra of dimension 2, which is non-abelian, so again, using this, you can construct a complex structure. So dimension 2 is well understood. So what happened in dimension 4? So in dimension 4, there exists 3 up to isomorphism. There exist 3 nilpotent Lie algebras, and one of them is this one. So you can consider a vector space of dimension 4 with this bracket. So at some point, the Lie algebra is going to be Heisenberg, because here we have a Heisenberg, plus R. This Lie algebra is easy to see, that is two-step nilpotent. And if we consider this endomorphism and then extend like this, so this is going to be a complex structure. The second one is the abelian Lie algebra of dimension 4 that admits a complex structure, and this one is the last one. So again, we have the space generated by this by this basis, and we consider this bracket. This is a 3-step nilpotent Lie algebra, and this Lie algebra do not admit a complex structure at the Lie algebra level. This was proved by Snow, but then Gauss and Ren proved that if you have an nilpotent Lie algebra of dimension n, which is n minus 1 step nilpotent, so this is 3 is 4 minus 1. So this Lie algebra will not admit a complex structure. So this is more in general. So dimension 4 for nilpotent Lie algebras, the existence of complex structure, it is well known. So there are some examples. So two of the nilpotent Lie algebras admit a complex structure, and the third one does not admit. Okay. I mean, not every nilpotent Lie algebra, not every Lie algebra admits a complex structure. Dimension 4, the solvable case, not nilpotent, is pretty well understood, was studied by Snow and Obando. Dimension 6, it is well known in the nilpotent case. So there are up to isomorphism 34 nilpotent Lie algebras, and only 18 admit complex structures. When we try to analyze what happened in the solvable case with which are not nilpotent, so there is a classification of the solvable Lie algebras, but there is no complete answer about complex structures. And what happened from dimension 8? So the following. So from dimension 8, in any even dimension, there are infinitely many nilpotent Lie algebras. So there exist curves of nilpotent Lie algebras, solvable Lie algebras, solvable Lie algebras. In particular, it's also true for nilpotent Lie algebras. And so what's the problem? So there is no classification. There is no class. So that is the first problem. So if you want to classify all complex structures on solvable Lie algebras, so the first problem is that there is no classification of these Lie algebras up to isomorphism. And the second one is that if you fix a solvable Lie algebra and you try to answer the question about the existence of an endomorphism satisfies these two conditions, that is also difficult to answer, because these two conditions are not linear. So at some point, so you can put the information in the computer, and maybe the computer will not stop. So those are the main problems. That's the reason so it's like this problem is considering while in that sense. And so then what is our hope? What is the best that we can do? Okay, the best that we can do is try to understand, try to study complex structures in some class of solved manifolds. And the idea of this talk is to study complex structures and symplectic structures on this class, which are called almost abelian Lie algebras. So what is the definition of an almost abelian Lie algebra? So this Lie algebras has an abelian ideal of codimension-one. Okay, so at some point, if you take your abelian ideal and then you take one element outside of that abelian ideal, you can write your Lie algebra fixing basis. You can write your Lie algebra as a semi-direct product of the element which is not in the ideal and the ideal, basically. So here I wrote R and Rm because I am fixing basis. And once you fix a basis, you have a matrix basically. So here you have the adjoint representation at E naught of E naught. And once you fix a basis, so you will have a matrix. Okay. The good thing is that this is so if you have this matrix A, so you have all the information that you need in order to understand the Lie algebra. Okay, so like all the information is encoded in this matrix A. So these are solvable Lie algebras. In particular, they are two-step solvable Lie algebras. That is pretty easy to see. And the Lie algebras are going to be nilpotent if and only if the matrix is nilpotent. Okay? So, so here, up to isomorphism, so what happened with these Lie algebras? So two almost abelian Lie algebras are isomorphic if and only if the matrices A and B are conjugate but up to scaling. Okay, so if we want to study up to isomorphism, so we need to study the conjugation up to scaling of the matrices. And in the nilpotent case, so two Lie algebras, two almost abelian Lie algebras are going to be isomorphic if and only if the matrices are conjugate. And this is because of the Jordan normal form, okay, using the Jordan normal form. So here, I would like to say a few things. So first one, so we are trying to say things about this, and we are going to work with class of conjugation of matrices. So at some point, we need to work with some matrices, and we are going to choose the Jordan normal form. Okay, and that is in this side. And here, if you have complex structure on one of these ones, so you are going to have a complex structure in the isomorphic Lie algebra, because all the statements are going to be written in terms of isomorphism or conjugation. And this is the notation that I am going to use. So I am going to denote by Jn lambda a Jordan normal block like this with eigenvalues lambda. And when lambda is 0, I am going to denote just like Jn. For matrices which are 0, so we are going to denote like this. So S is going to be the size of the matrix. And I am going to denote like this with this sum, these block diagonal matrices. Okay. So then if you have a nilpotent matrix which is not 0, so then A will be conjugated to a matrix like this. So this is basically the Jordan normal form of A. Okay. And from now on, I am gonna work on this class of matrices. So A here is a number, a real number. B is a vector, and capital B is a square matrix. And if this has dimension n to n, This V will have dimension 2n, no, 2n minus 1. This V will be of size 2n minus 2. And if you consider matrices like this, which are nilpotent, A is going to be an eigenvalue, so A has to be 0, and B has to be nilpotent. And this is if and only if. And the first result that I want to mention is this one. So consider capital V a nilpotent matrix, and W one vector in the image of capital V. So our first statement says that if you consider this matrix, so this matrix will be conjugate to this matrix. So if W is in the image of capital B, so then you can add W here, and you are going to be in the same class of matrices up to conjugation. Okay. So if in particular, if B is in the image, if B is in the image of capital B, so then minus B is going to be in the image of capital B, and then, so here, I can put a 0. Okay? So at some point, if B lies in the image of capital B, so in our notation, we are going to have that this matrix is conjugate to this one. Why this is important? Because so we prove this proposition first. So here, so I am considering a matrix C like this, and here I wrote the Jordan normal form of B like this. So then, so we have there are not three possibilities, but then C is conjugate to one of the following matrices, and here we have 3 cases. Okay, so the first one is the case that I mentioned in the previous slides, so when B is in the image of capital B, but then if B is not in the image of capital B, so we have different cases. So the second one, basically, if you see this case B, so the Jordan normal form of C is almost the same than the Jordan normal form of B, but look at here. So one of the Jordan blocks of this JMD disappear because here we have -1, but appears this Jordan normal block which has size 1 more than JMD. And in this last case, one dimension of this big 0 disappear and appears a J2. I am going to give you an example. So these are basically examples each for each of these cases A, B, and C. So imagine that this is capital V. So this is capital V, and this is V. If B is in the image, so then I told you in the first result that you can up to conjugation you can put a 0 here. So then you have so here you have a J3, and here you will have with this and this 102. Okay. But if you have here a V which is not in the image of this capital V, in this case, it is just an example, Look at here. So 1 for this V. So this J4 appears. So this is up to conjugation. We have J4 plus O1. And in the last case where one J2 appear, if you look at here, so here we have a J3, and if we consider here, so we have a J2, okay? So why this is important? Because here we have this result of Jorge Lauret and Edwin Rodriguez Valencia, speaking about when an almost abelian Lie algebra admit a complex structure. And this is if and only if M is conjugate to a matrix like this, where this capital B satisfies, so belongs to this set, where this JM is this one. Okay, so the idea of the following is try to understand how looks this set, and once we understand this, so we will try to understand what happened with the with this matrix up to conjugation. Okay, and the first proposition that we prove, and here in the nilpotent case, so all of these blocks have a 0 eigenvalue. So if you take a V written in the Jordan normal form like this, so then some capital V, so this capital V is conjugate to a matrix in that set, in the set that we want to study, if and only if S, that is the size of the big zero, and Qi, which are the exponents of the blocks, all of them are even. So now we understand how looks the Jordan normal form of a V line in this set. And with this information, we are going to try to understand what happened with our matrix C. And this is our first theorem. In the nilpotent case, so if you consider a matrix M written in the Jordan normal form like this, so then GM will admit a complex structure if and only if one of these three cases happens or holds. And all of them are written in terms of this, the exponents are the size of the big zero. And of course, they are in correspondence with the three cases that I spoke about in a previous proposition. Okay, so basically, this is the case when is in correspondence with the case in which I am going to write here. No, this is 0, 0, B. So the first case is in corresponding with the case when B is in the image of capital B. So this is in correspondence with the case in which J2 appears, and this is the other case. Okay. But what happened in the general case? Because this is just the nilpotent case. So what happened in the general case? So here, I will need to introduce more notation. So, so here I am gonna study what happened with a matrix which has only one eigenvalue, and that eigenvalue is real and it is B. So A will be conjugate to to one matrix like this. So this is the normal Jordan form, or like this if it's a multiple of the identity. So with the size of the blocks and the exponent and the size of the identity, we will define this lambda, and in this case lambda will be m. So this is just the case when A has one eigenvalue and it is real. Of course, we can have this other case where the eigenvalues of A are complex, and only we have this, in this slide, we have only these two eigenvalues. So we wanted to write A up to conjugation in a similar way that when B was real. So here we have to consider these matrices, and then this canonical form of matrices, which are real. Okay, so then A is going to be conjugate to a matrix like this or a matrix like this. Okay, and again we can define lambdas here. But in general, so we can have matrices with real eigenvalues and complex eigenvalues and difference. So here I am gonna denote, so by the first lambdas are the real L lambdas are real eigenvalues, and then we will have the complex eigenvalues here, and so a matrix C is going to be conjugate to something like this, in which this basically is the part of the matrix which only has eigenvalue lambda 1, and then the part of the matrix which only has eigenvalue lambda 2, and so on. Okay, the last ones are with the complex eigenvalues. And again, we need to understand what happened with matrices commuted with this Jm, or commuted with some J satisfying this equality. And in this case, the characterization of this set is a little bit well, it is this one. So basically, V is conjugate to a matrix in this set that we are interested, if and only if for any real eigenvalue of B, the following conditions are satisfied. And then if you look at lambda, when you consider one of the eigenvalues, so the lambda has to be like this, with T and Pi, all of them even, or in the case that you are in a multiple of the identity, so the size of that multiple has to be even. So now we understand what happened with B. So at some point we had something like this. So we understand pretty good what this part. So now we want to consider the whole matrix. And first, we prove this result in where we only consider matrices which has eigenvalue A, and A is real. So we could prove that GM admits a complex structure if and only if this matrix, which is nilpotent, because we are subtracting all the eigenvalues A, admit the complex structure. So at some point, if all the eigenvalues are the same, JM will admit the complex structure if and only if the nilpotent part admit the complex structure. And in general, you can have, I am gonna write again here, A, B, like this. So A is always an eigenvalue, but then here, so you can have on B some eigenvalues which are A or not. So in general, you can write a matrix like this as a sum of the part which only has eigenvalue A and the part which we do not have A as an eigenvalue. And then JM will admit a complex structure if and only if this part, so GMA admits a complex structure, and then this Q basically lies in one of these sets. So this Q commute with some J, basically. This is satisfy this, basically satisfies this for any real eigenvalue B. So at some point with this, so with this result, we completely understood so when almost abelian Lie algebra admits a complex structure, okay? And I was like too slow, so but I'm going to stop here because I don't. So I'm not sure. So how much time do I have, Adrian?
Like 8 or 9 more minutes.
Okay. Okay. So I'm going to say a few things about the symplectic structures. Okay. So this is a definition of having a symplectic structure on a Lie algebra. So basically, a symplectic structure is to form non-degenerate to form, which is closed. And here I wrote what is the derivative. And again, the situation is analogous to the complex situation in the case that dimension 2 is well understood, dimension 4 is well understood. From dimension 6, the problem starts and try to classify which are the Lie algebras admitting symplectic structure is a wild problem. That's the reason, again, we restrict ourselves to these almost abelian Lie algebras. And here we have a similar result, or an analogous result than in the complex case. So this was proved by Lauret and Will. And an almost abelian Lie algebra admits a symplectic structure if and only if now M is conjugate to a matrix of the same form that in the complex case, but now with B lines on SP. Okay, so now we need to understand how looks the matrices line here. So again, we have a result in the nilpotent case. So this theorem was proved by these people. And if you restrict, if you consider a matrix written in the Jordan normal form, so then B is going to be conjugate to a matrix on SP if and only if S is even, again, and the exponent QI are even, but for all I, such that MI is odd. Okay, so there is a relation between B which are complex and B which are lies on SP, and this relation is going to be later I'm gonna tell you how this relation is reflected in one result. So again, we can prove a result as an analogous result on the nilpotent case. And now we have two cases. So in almost abelian algebra, we admit a symplectic structure if and only if one of these conditions holds. Look at here, this odd, again, something analogous to the complex case, but now here P is even for all odd and I. This is basically the case in which we have a capital, we have a V line on the image of capital B, and this is other case, so I do not have time to explain, but basically this is a classification theorem in the nilpotent case. But then, of course, when we want to study what happened in the general case, we need to study what happened with V lines on SP. And here, the characterization of this V, written in the Jordan normal form, are like more difficult, I don't know, to write. So any lambda in the eigenvalue of capital B has to satisfy these things. If lambda is equal to 0, so basically we are considering a block or many blocks with eigenvalue 0. So then the condition is the same than in the nilpotent case. But if lambda is not a pure complex eigenvalue, so then minus lambda has to be an eigenvalue of capital B. And there is a relation between lambda, big lambda, capital lambda, of B minus lambda and B of lambda. So now we understand and we analyze, we study what happened with this V. So we understand this part. And now we want to understand what happened with this, with the whole matrix, basically. And then, again, we have to analyze two cases. Or here, first we analyze this case, basically, because if you look here, if you have if lambda is an eigenvalue, in these cases, minus lambda is going to be an eigenvalue. So here, basically, we are analyzing what happened when we have only matrices with the eigenvalues A and minus A. And here we could prove that an almost abelian algebra admits a symplectic structure if and only if this JM M tilde admits a symplectic structure. And here, because the eigenvalues here are A and minus A, basically this M tilde is nilpotent. So at some point, in order to understand when this almost abelian algebra admits a symplectic structure, we need to understand what happened when the matrix is nilpotent, and we understood that in the previous slides. And so this is basically the general case when we have one part of the matrix with eigenvalue A and one Q where A is not an eigenvalue. So in the case, so basically here, I am going to write like this again. If A if A is equal to 0, so then capital B can have a 0 as an eigenvalue. So then we can write M like this, and then GM will admit a symplectic structure if and only if the nilpotent part admits a symplectic structure, and Q lies on SP. This is basically the case in which A is not an eigenvalue of B. And this is the case in which B has, so expect. And this is the case in which A belongs to the spec of B, so then minus A has to be in the spec of B too. And here we could prove that it's gonna admit a symplectic structure if and only if the nilpotent, this part admits a symplectic structure that we understood in the previous result, and Q is in SP. And so here I want to show you some consequences. For instance, if you, from these results, if you consider almost abelian Lie algebras, which are nilpotent, k-step nilpotent for k equal to 2, 3, and 4, then all of them admits a symplectic structure. In dimension 8, which is the first case in which everything started to be wild, almost abelian nilpotent Lie algebras admits a symplectic structure. The first dimension, in the nilpotent case, the first dimension in which an almost abelian Lie algebra do not admit a symplectic or a complex structure is dimension 8, and the only M satisfying this is this one. And here, this is the relation that I mentioned. I mentioned in some of the previous slides. If M is nilpotent and GM admits a complex structure, then it's going to admit a symplectic structure. This is only in the nilpotent case. It's not true in the solvable case. And if you want, if you want examples in which the converse is not true, so we have these families of matrices satisfying that GM admits a symplectic structure but not a complex structure. And I am going to stop here because I am over time. Thank you.
Okay. Thank you very much, Romina. Nice talk. Now, I have to put my camera. Okay. Yes. Are there any questions or comments for Romina? I guess there are, so it's true that there are more symplectic, almost abelian Lie algebras than complex ones. That's
in the nilpotent case.
In general, also the solvable case. Nilpotent case, yes.
It seems to be, yeah, there are more. But for instance, in the nilpotent case, yeah, in the nilpotent case is also true, but so as I mentioned here, so this is only in the nilpotent case. So at some point, if you consider the solvable case, so there could be intersection between admitting complex or symplectic, but then the sets of Lie algebra could be different, but in all dimensions and examples that I know, I would say that there are more symplectics than complex, but they just, yes.
Okay. And one more thing, did you consider the existence of lattices in the Lie groups associated to these Lie algebras?
So in an important case, all of these
Uh,
admits lattices, of
yes.
course. So you can consider compact quotients, for instance. But in the solvable case, we, we, we didn't study the.
Well, they have to be unimodular, and I guess that the A has to be 0, right? For the complex case, at least, but I'm not sure.
A has to be 0?
I think so. Well, in the hypercomplex case, that happens.
Sí, cierto.
But well,
Why? Why it has to be 0?
properties with polynomials.
Ah, ah.
Well, it could be something to see.
Sure.
Are there any other questions or remarks for Romina? Well, if not, let's thank her again. Okay. Thank you very much, Romina. Now you can go to have your lunch.